Welcome to this session. This session, we are going to discuss the first property of Jacobians and prove it. So the property states that if u and v are functions of x and y, then the Jacobian of uv with respect to x and y times Jacobian of x and y with respect to uv is 1. So please, this does not mean that you cross in this partial u v partial uv and you say 1 1 and then partial xy 1 1. That will take you to hell. So let's see how we need to prove this. So proof. So we say let u be a function of x and y and v be also a function, say phi of x and y. Call this one equation 1, call this one equation 2. But let those two u and v be functions of x and y. Now, we know from definition that partial or Jacobian of uv with respect to x, y is given by partial u, partial x, partial u, partial y, partial v, partial x, partial v, partial y, and partial x, y, partial uv, or the Jacobian of xy with respect to uv is a determinant partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. These are from definition. So this implies that when they tell us that we are multiplying these two Jacobians, times Jacobian of xy with respect to uv is the same thing as this determinant, partial u, partial x, partial u, partial y, partial v, partial x, partial v, partial y, you multiply by partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. Let's call this one question 3. Okay, so in this proof, it is assumed that you know properties of multiplication of two determinants. So if you don't know them, please watch videos on linear algebra so that you know what's happening. Now, the task now will be to evaluate this determinant. And remember, one of the properties of determinants is that determinant of a matrix is the same as the determinant of the transpose of the same matrix. So we say transposing the second determinant in 3 we have now, because transposing doesn't change the value of the determinant, so there's nothing we're changing. So the sign remains to be the same. So we'll have partial uv partial xy times partial xy partial uv. So we are not interfering in the first determinant. So we have partial u, partial x, partial u, partial y, partial v, partial x, partial v, partial y. So what we are doing is to transpose the second determinant, meaning that rows becomes columns and vice versa. So times. So we'll have partial x, partial u, and then this becomes here partial x, partial v, and then partial y, partial u, and then partial y, partial v. So there's nothing we have changed on the value of the determinant. Transpose of a matrix doesn't change the value of the determinant of the same matrix. Now, if you remember on properties of multiplication of two determinants, then we multiply rows of the first matrix or first determinant with rows of the second determinant, not rows and columns like in the usual matrices. So this will give us this row times this row. So we'll have partial u, partial x times partial x, partial u, plus this element and this partial u, partial y times partial y, partial u. And then here we'll have this first row times the second row. So we'll have partial u, partial x, partial x, partial v, plus this element times this. So partial u, partial y times partial y, partial v. And here we'll have this row times this row. So partial v, partial x times partial x, partial u, plus this element times this element, partial v, partial y times partial y, partial u. Here we'll have this row times this row, partial v, partial x, partial x, partial v, plus this by this, partial v, partial y by partial y, partial v. So that is how we multiply two determinants. If you don't know the procedure, please check the linear algebra work. So that's what we have. Let's call this one, this expression, call it number 4. Now, differentiating, when differentiating, one and two, partially with respect to u and v, we have, so remember 1 and 2 are these functions here. U is a function of x and y, v is a function of x and y still. So because they are functions of several variables, then we'll use chain rule to carry out that differentiation. So we'll have, so if you don't know how chain rule works, please check the work done in calculus, a function of several variables. So partial u is the same as partial u partial x, partial x, partial u, and then plus partial u, partial y, and then partial y, partial u. So that's what we have. And then, so this partial u is 1. And then partial u, partial v is the same as partial u, partial x times partial x, partial v plus partial u, partial y times partial y, partial v. And because u is only a function of x and y, so when you get partial u, partial v, the answer should be 0. And then partial v, partial x, partial v, partial u is the same as partial v, partial x, partial x, partial v, partial u plus partial v, partial y times partial y, partial u. So this is u. And you see, because v is only a function of x and y, so when you get partial with respect to u, the answer should be 0. And then partial v is the same as partial v, partial x times partial x, partial v plus partial v, partial y plus partial y, partial v, and partial v, the answer is 1. So please remember that what's happening here in this expressions, we are using chain rule for function of several variables. So this is chain rule. So if you don't understand how these ones are coming, please watch the videos on chain rule for function of several variables. So then now, if we call this one, this set, we call it 5. So replacing 5 in 4, we have, so remember this is 4. So partial u, this is what was representing 1. If you check 5, this is what we have gotten the answer to be 1. This is what you have gotten the answer to be 0. This is what you have gotten the answer to be 0. This is what you have gotten the answer to be 1. So therefore, partial uv, partial xy times partial xy, partial uv is the determinant 1, 0, 0, 1. And this answer is 1. So that's how we prove that property. Thank you.